Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
When you think about Mars, the image that instantly pops into your head is the red planet. It's dusty, it's cold, desolate, and just utterly, profoundly dry.
Right, it's the planet of rust, of a thin, wispy atmosphere. And we think of its surface as being carved by wind, not water.
And it's looked that way for eons, billions of years. But here's the thing, the shift in perspective that we really need. Ancient Mars.
Yeah.
It was dramatically, fantastically wet.
Oh, absolutely. It had water flowing, collecting, and eroding in volumes that we are, only now really beginning to quantify.
And that quantification, that's the essential leap forward here, isn't it?
It is. For decades, the debate was really just centered on the existence of water. Was it there?
We spent so long just looking for the smoking gun.
Exactly. And now the question has shifted entirely. It's about scale. It's about structure. It wasn't just wet. It was, and this is the key word, organized.
Organized. What do you mean by that? Was it just random pooling or?
Yeah. Well, that's the question. Was it just isolated flash floods from, say, a meteor impact melting some ice? Or was it sustained, integrated, almost Earth-like hydrology?
And that is precisely what we're deep diving into today. We have this foundational new study from scientists at the University of Texas at Austin, UT Austin, and it's just been published in the Proceedings of the National Academy of Sciences.
And this isn't just another paper confirming water. We're so far beyond that now.
This is the first systematic, truly comprehensive mapping of Mars's ancient major river basins. It's watersheds. It's giving us a colossal measure of their past power.
So our mission here is to take this new high-tech planetary cartography and really use it to gain insight into three crucial areas. First, just the sheer, almost unimaginable volume of water ancient Mars held, and like we said, how it was organized.
Okay.
Second, we need to understand the tools. The really ingenious techniques combining old data with new imagery that scientists used to map rivers that vanished billions of years ago.
And
finally, we have to tackle the most compelling mystery that all this new evidence raises. We're going to review the current scientific consensus on where all that water went.
Okay, let's unpack this then. We're talking about an immense planetary plumbing system, one that's been completely silent, dormant for geological ages. So to set the scale for you right at the top, here's the initial shock factor nugget from this study. This first-of-its-kind mapping identified major drainage systems that produced an estimated, get this, 28,000 cubic kilometers of sediment.
28,000 cubic kilometers. That is a number that forces us to completely recalibrate our models of early Mars.
It's not just a little adjustment.
No, not at all. We are not talking about mere streams or temporary ponds. We are talking about Earth-scale continental river systems capable of eroding and transporting that mind-boggling volume of material across vast distances on another world.
Just to give you an idea of that size, 28,000 cubic kilometers is roughly enough sediment to completely bury the state of Texas.
Wow.
To bury it under a layer of dirt 100 feet deep.
100 feet.
That's the sheer scale of the erosional power we are dealing with. So, okay, we're moving from this general, abstract idea of water to the specific organization and structure of these water systems. We know the water was there. But what does the organization of that water tell us about the climate on ancient Mars? I think this is where the new study really provides the critical insight.
It's the difference between finding, say, a small, isolated stream bed in the desert.
Right.
That might have been caused by one single heavy rain.
Yeah.
It's the difference between that and mapping the entire Amazon River basin.
Which requires
thousands, maybe millions of years of continuous, predictable climate patterns. And Dr. Timothy A. Gouge, who led the research, he encapsulated this finding perfectly. He said that while we've known for a long time there were rivers on Mars, he said, and I'm quoting here, we really didn't know the extent to which the rivers were organized in large drainage systems at the global scale.
Okay, let's dig into that. Why does that organization, that structure, why does it change the entire debate? Why is it such a monumental leap forward compared to just finding more evidence of flow?
Because organization implies sustained, consistent hydrological cycles.
Okay, an actual cycle.
Like on Earth.
Exactly like on Earth. Think about our planet. When you see a massive, dendritic watershed.
Dendritic meaning tree-like, right? Like branches.
Precisely. Where smaller streams feed into tributaries, which then feed into major rivers, which eventually empty into an ocean. That whole geological structure, it's the accumulated result of millennia of stable weather. It means precipitation was consistent enough to feed the entire system. Runoff was predictable. And the system itself was stable enough to carve deep, integrated channels over a very, very long time.
So if the water was only caused by these random episodic events, like a massive asteroid impact melting a bunch of ice or a huge volcano going off, you just wouldn't get that integrated structure, would you? You wouldn't. Not at this scale. Those chaotic episodic events, they create isolated channels or massive outflow features. Sure, we see those on Mars.
Right.
But they don't produce a sprawling, globally scaled network of interconnected systems that drain thousands of square kilometers in a coordinated way. This kind of integrated system. It confirms the presence of a climate that could sustain large-scale, stable river flow over long periods. And that makes the ancient planet much more Earth-like than some of the colder, drier models previously suggested.
And it's important to note, these researchers weren't just looking for small, localized streams. They intentionally set a very high bar for what even qualified as a system worth mapping.
That's a crucial point. They were specifically hunting for the planetary heavyweights.
So what was the threshold?
To define a scale, they established a specific methodological threshold for inclusion. They only mapped drainage systems that exceeded 105 square kilometers in surface area.
That sounds incredibly precise. 105. Why that specific area? Is it arbitrary?
Not at all. It's a crucial methodological anchor. 105 square kilometers is a common baseline area used in geology for defining what qualifies as a large drainage system right here on Earth.
So they're using our own planet as the yardstick.
Exactly. By using this comparable terrestrial threshold, they weren't trying to capture every small gully that might have been created by some seasonal melt. They were systematically looking for features that qualify as major rivers, as large-scale drainage basins, the kind of systems that define the regional climate and geology of a planet.
So it ensures that what they're studying on Mars is comparable in scale and in its implications to a significant river system we'd recognize today.
Right. By using that 105 square kilometer standard, they are essentially saying, if this system were on Earth, it would be a major hydrological feature we would study in depth. It forces the conversation away from any marginal, maybe temporary water activity.
It puts the focus squarely on the systems that did the heavy lifting, the ones that really shaped the surface.
It absolutely does. And it supports a central tenet in geology we call uniformitarianism.
The present is the key to the past.
The very same idea. The same natural laws and processes that operate today operated in the past. So if a system of a certain size requires a sustained climate here on Earth, it almost certainly required a sustained climate there on Mars.
And this systematic approach also meant they had to define exactly what components constituted an organized system. They weren't just looking for wiggly lines on a map.
That's right. A watershed is a holistic unit. It's not just a single channel. So they listed 4 key components they needed to successfully map and link across these vast areas to declare a system organized and, major.
What were those 4 defining components?
Okay, so first, the river systems themselves. That's the main channels, the smaller tributaries flowing into them, that whole dendritic network structure we talked about.
The branches of the tree.
Right. Second, the water deposit systems. These are the region, often big sedimentary plains, where the water lost its speed and started to deposit its carried load of sediment.
So the source and the sink, the beginning and the end of the line.
Exactly. Third, the outlet canyons. These were often dramatic, high-energy exit points where massive volumes of water escaped a basin, potentially flowing out to the vast northern lowlands of Mars.
And the 4th piece?
And fourth, the lakes and valley networks. These represent the temporary, or in some cases long-term reservoirs where water accumulated before either evaporating or flowing out through one of those outlet canyons.
It's just fascinating that they needed to find all 4 of those elements connected together. That really demonstrates an integrated structure.
It does.
By linking all those arteries and veins together across these huge areas, they essentially move the needle from, okay, Mars had water, to Mars had a functioning planetary scale hydrological cycle.
And it confirms a period of Martian history where precipitation and surface conditions were just fundamentally different. To sustain 16 of these massive systems requires more than just occasional melt. It requires a warm enough surface and a dense enough atmosphere for water to flow, collect, and erode across enormous distances. It confirms a vast, ancient, and very active history for the planet.
Now, we get to a part of this that I find truly intriguing. Here's where it gets really technical and I think really inspiring. How exactly do scientists map the beds and channels of rivers that vanished literally billions of years ago?
Right.
Rivers that are now potentially buried under shifting Martian dust or thick lava fields or these massive wind-blown deposits. We are relying entirely on remote sensing, on orbiting instruments for this historical reconstruction.
And this specific mapping effort is just a masterclass in combining different types of orbital data. It's really clever. To reconstruct ancient water flow, you need two crucial high-precision pieces of information. You need to know where the ground is, so extreme precision on altitude.
The topography.
The topography, exactly. And you need a high-resolution visual proof of what is actually on the surface.
Okay, let's start with that foundational data set, the altitude component. The study relies heavily on an instrument called MOLA.
Yes, the Mars Orbiter Laser Emitter. MOLA was a primary instrument on board NASA's Mars Global Surveyor, which operated successfully from 1997 all the way to 2006.
So this is legacy technology we're talking about.
It is, and it's a revolutionary piece of legacy technology. MOLA works by firing a laser pulse down at the Martian surface and then timing exactly how long it takes for that pulse to bounce back to the spacecraft.
So it's basically like a super precise tape measure from space.
That's a great way to put it. By tracking millions and millions of these pulses globally, you can calculate the distance and map the topography of Mars with extraordinary precision.
So MOLA provides the bedrock map. It defines the continental divides, the lowest points, the high points. Crucially, it tells us which way water would have flowed just based on gravity.
Exactly right. You simply cannot define a watershed without incredibly detailed altitude data. The sheer precision of MLA, which is often capable of measuring altitude differences down to the meter or even sub-meter scale.
That's incredible.
It is, and that's what allowed the scientists to mathematically model the subtle, faint gradients of a 4-billion-year-old riverbed that might have been partially eroded or buried. It defines the paths of least resistance for every theoretical drop of water across the entire Martian surface.
So MLA provides the mathematical framework for the flow paths.
Yeah.
But altitude data alone doesn't prove that a river was actually there, right? Or that the feature wasn't carved by something else like lava.
An excellent point.
You need the visual confirmation, the proof that the flow was indeed fluvial, water-based, and that's where the CTX, the context camera, comes in.
Yes. The context camera is currently orbiting Mars on board the Mars Reconnaissance Orbiter, or MRO.
Which is still active.
Still very active. And CTX is critical because of its scale. Now, there are other cameras on MRO that take higher resolution snapshots, like the famous HiRISE camera, but CTX's distinction is its sheer volume of data and its medium resolution coverage. It has achieved nearly complete coverage of the entire red planet.
So MLA tells you where to look for a drop in elevation, and CTX provides the high-resolution imagery you need to actually identify the erosional features along that path.
Precisely. CTX confirms the geological reality. It allows researchers to identify the detailed structures. You can see the actual river bends, the meanders. You can see layered sedimentary deposits on the valley floors. You can see those subtle dendritic or tree-like branching patterns of the valley networks that are so characteristic of organized water erosion.
The combination is just so powerful.
It really is. You use MLA to trace the flow direction, and then you zoom in with CTX to confirm that the features along that path are indeed ancient river channels.
And the beauty of it, as you said, is that this study synthesizes data separated by decades. It really proves the continuing value of NASA's long-term investments in these missions.
Absolutely. The data from Mars Global Surveyor is still generating groundbreaking science today.
But how do you actually reconcile and overlay these massive, complex data sets? This is where the specific software comes in. The source mentions they used ArcGIS Pro.
And this is an important detail for you, the listener, to note. ArcGIS Pro is a commercial, industry-standard geographic information system, a GIS. It's used by cartographers, city planners, geologists all over the world for Earth.
So it's off-the-shelf software.
It is. And the fact that planetary scientists use this same software underscores the universality of their methods. They're using the same tools to map Mars that someone might use to map a new highway system in Ohio.
So how does that software bridge the gap between MOA's data and CTX's images?
It allows for seamless data layer integration. In a GIS, you can treat MLA's topography data as one massive layer. That's your elevation map. Then you can overlay CTX's visual imagery as a second layer right on top of it.
And you can add more layers, I assume.
Oh, yeah. You could add a third layer for mineral mapping, which we'll get to later. A fourth layer defining those 105 square kilometer catchment boundaries. And ArcGIS Pro allows researchers to define parameters. You can tell it, show me all the features from the CTX images that exhibit dendritic patterns A and D, whose lowest point connects to the mathematically predicted flow path we derived from the MLLA data.
So it automates the search, in a way.
It makes the search systematic, objective, and reproducible. It moves planetary geology into this new era of verifiable cartography, using the exact same tools we use to manage resources right here on Earth.
And this systematic, rigorous mapping methodology is what gives these hard numbers their weight, their authority. So let's shift our focus now entirely to the tangible results, the specific measurements, and the sheer impact of these ancient river systems on the Martian surface.
Okay. The findings derived from this MLA-CTX fusion are remarkably clear. The researchers successfully mapped 16 highly organized drainage systems that exceeded that 105 square kilometer baseline.
15 of them.
16. And these are not just suggestions of waterways. They are now the acknowledged major integrated continental scale hydrological features of ancient Mars.
And once again, that sediment volume, 28,000 cubic kilometers of material. We'll have to spend some more time on this number because it really is the core measure of the water's power. Can we try and quantify that volume with some more vivid Earth-based analogies?
We have to. It's the only way to grasp it. The sheer volume moved by just these 16 systems, it's comparable to the mass of a small terrestrial mountain range. So instead of being lifted up, it was transported across the surface.
Wow.
Here's another way to think about it. If you took all the water in Lake Superior, which is the largest of the Great Lakes by volume, the sediment moved by these Martian systems is equivalent to filling Lake Superior approximately 3 times over with packed dirt and rock.
3 Lake Superior's worth of dirt.
Just moved by water. That is a stunning measure of the erosional work done by Martian water during its wet periods.
That is a staggering amount of material to move. It's so hard to imagine that level of fluvial erosion on a planet we think of as static and frozen.
It is.
But the context becomes even sharper when we look at the relative contribution of these 16 systems to the total planetary history.
Which brings us to the 42% figure.
Right.
The study concluded that these 16 mapped systems comprise approximately 42% of the total flowing sediment volume across all of ancient Mars. And this is arguably the most crucial takeaway regarding the nature of Martian hydrology.
Okay, let's stop there and really analyze that. 42%. If Mars had potentially thousands of smaller, unorganized streams, creeks, and flash flood events, which we know it did, how can just 16 large systems account for nearly half of the planet's total fluvial work?
It speaks directly to the efficiency and the duration of the flow in those systems.
The power was concentrated.
Highly concentrated. Think about it. 16 systems doing almost half the work. That means these specific systems were disproportionately powerful. They had to have operated consistently, efficiently, and for a very, very long time. It strongly suggests that while episodic water events might have initiated some erosion here and there, the bulk of the planet's surface sculpting was done by these massive integrated drainage systems.
And those systems would require a stable climate regime.
A sustained water cycle, perhaps involving rain or snow, something to keep them flowing for potentially millions of years.
So instead of a picture where water was just kind of everywhere carving millions of small gullies, the picture shifts. It becomes one where water was highly concentrated in a few dominant continental basins that really dictated the planet's geological evolution.
Precisely. If on Earth, 42% of all the fluvial work were done by only 16 rivers, the Amazon, the Nile, the Mississippi, and a few others, that would imply a global uniformity in topography and precipitation that we just don't see. The fact that the Martian system is so concentrated suggests one of two things. Either Martian topography was incredibly efficient at funneling precipitation into a small number of giant basins, or the global climate was remarkably stable, allowing only the largest systems to operate long enough to accumulate that massive sediment volume.
That concentration of power is immense, and it must offer important constraints for climate modelers, for the people trying to recreate what the ancient Martian atmosphere must have been like to sustain these giants.
Absolutely. It narrows the possibilities.
The study also had a specific finding about the role of the outlet canyons, those dramatic exit points of these systems.
Yes. They quantified the impact of these high-energy features, and they discovered that the outlet canyons, the points where large bodies of water, like lakes, breached or overflowed, contributed approximately 24% of the global river sediment amount on ancient Mars.
Okay, let's put those two numbers together. We have 42% from the sustained large-scale river flow within the basins, and 24% from just the outlet canyons.
Right.
That 24% implies massive, focused, potentially catastrophic flows where the water exited the basin. How do we reconcile those two things? Does this mean Mars was both sustained and catastrophic?
I think it paints a very dynamic picture. The 42% confirms the consistency, the long, slow work of erosion and transport inside the basin. But the 24% from the canyon suggests that these basins, which likely held massive lakes, occasionally breached or overflowed in huge, violent volumes.
So the system would fill up slowly over time.
Exactly. It implies that the water flowed consistently, filling up giant, long-lived lakes, which then sometimes reached a catastrophic tipping point of discharge.
Good.
These canyon exits acted as high-speed funnels, transporting massive amounts of material from the interior basins down to the northern lowlands. And that likely contributed to the formation of whatever ancient oceans or major bodies of water may have existed there.
So slow accumulation, punctuated by high-speed discharge. It suggests the Martian water cycle wasn't just stable, it was also capable of producing these immense focused floods at the termination points of these megasystems.
It makes a lot of sense. Imagine a massive reservoir filling slowly over 1,000 years, then suddenly breaching a natural dam. The consistent work of filling it is the 42%. The dramatic breach is the 24%.
It confirms a truly powerful and very active hydrological cycle operating at an immense scale. Before we move on to the great mystery of where it all went, let's ground this new cartography in the context of the overwhelming evidence that already confirmed ancient liquid water dominated the Martian surface.
That's right.
This mapping is new in its scope, but it really builds on decades of geological and mineralogical proof.
That's the key point. This study confirms the system was integrated, but the physical proof of water has been piling up since the Viking missions in the 70s, and it just escalated exponentially with the rovers.
And that proof comes in two main forms, right? The shapes on the surface and the chemical residue left behind.
The geomorphology and the mineralogy, exactly.
Let's start with the geomorphological landforms, the geological evidence of liquid movement besides these drainage systems. What are the classic undeniable signs of past water that we see from orbit?
Well, we see clear evidence of deltas. The most famous right now is the incredibly well-preserved delta structure in Jezero Crater, which is exactly why the Perseverance rover is operating there.
Right.
Deltas only form when a flowing river slows down rapidly and dumps its sediment load as it enters a large standing body of water. That means there had to have been a long-lived lake or even a sea in that crater.
What else?
We also see massive outflow channels. These are immense scars on the surface, sometimes hundreds of kilometers wide. They're often associated with catastrophic flood events, likely from the rapid release of pressurized underground reservoirs.
And on a smaller scale, we see smaller features too, don't we?
Oh, yes. Thousands of small-scale features like gullies. You often find these on crater walls, and they may represent more recent seasonal flows or maybe just near-surface ice melting. And maybe most evocative for suggesting large standing bodies of water, we see evidence of coastal-like terraces. These are horizontal markings, almost like steps in the landscape, suggesting ancient shorelines where water stood still at a consistent level for extended periods, perhaps defining the boundaries of an ancient northern ocean.
So those landforms tell a story of movement, stillness, and massive flooding. But the most undeniable proof, I find, comes from the chemical signatures, the mineralogical evidence that only forms in the presence of liquid water.
The minerals are the chemical fingerprints of the water's composition and its history. They are the archives of that wet phase.
And we found several key types identified by orbiters and then confirmed on the ground by rovers.
We have, first, clays, or what geologists call phyllosilicates. These form when water interacts chemically with volcanic rock over prolonged periods. The very fact that they exist suggests relatively neutral or alkaline water conditions, which is, potentially favorable for life.
But Mars clearly changed because we also found minerals that suggest a highly acidic environment later on.
That's right. We find vast deposits of sulfate minerals and carbonates. Sulfates in particular often precipitate out when water is acidic and evaporates rapidly.
So the minerals themselves tell a story of climate change.
They provide a geological timeline. They confirm that the Martian water cycle not only existed, but it also changed chemically as the planet cooled and its atmosphere thinned. You had clays forming early in a more benign environment, then sulfates forming later in a harsher one.
And of course, you can't talk about water evidence without mentioning the tiny, infamous hematite blueberries.
The favorite piece of evidence for so many people. These small, spherical concretions of iron oxide, they were famously discovered by the NASA Opportunity rover way back in 2004, just scattered all over Meridiani Planum.
And they could only have formed in water.
Hematite strongly indicates formation in the presence of water. Likely as minerals precipitated out of a flowing, slightly acidic solution, they are the perfect, small-scale, undeniable proof of prolonged aqueous activity on the surface.
So, okay, we have the geomorphological structures, we have the chemical signatures, and now we have the global map of 16 giant river systems. This whole body of evidence leads us to the crucial timeline debate. When did all this incredible activity happen, and for how long?
Mars formed with the rest of the solar system roughly 4.5 billion years ago. The generally accepted wet period, what we call the Noachian period, occurred relatively early, within the first billion years or so. But the specifics, especially how sustained that wet period was, that's still intensely debated.
Let's elaborate on those two main schools of thought.
So on one side, you have scientists who argue for episodic periods of water. This model suggests that while water existed, warm and wet conditions were transient. They were a flash in the pan.
So a frozen Mars with brief thaws.
Exactly. Perhaps massive impact events or intense volcanic eruptions released enormous amounts of greenhouse gases, which temporarily warmed and thawed the surface. That would allow water to flow violently for maybe hundreds or thousands of years before the planet froze again into its default cold state.
And the other side argues for a more sustained period.
Yes, the argument for a lone longer period. This suggests that early Mars maintained a thick enough atmosphere and sufficient heat, probably via a CO2 greenhouse effect, to sustain liquid water continuously for hundreds of millions of years.
And this new study, with its 16 large integrated systems, that must lend some serious weight to that longer period model.
It really does. It's hard to imagine carving those massive systems with just a few thousand years of flow here and there. It requires immense cumulative flow time.
And the most recent data on this really pushes that timeline. I mean, it pushes it far into the planet's history, doesn't it?
It does. The source mentions a 2022 study that estimated Mars had liquid water as recently as 2 billion years ago.
2 billion. That's more than halfway through the planet's history.
It is a stunning longevity. If that timeline holds true, it suggests water persisted in significant quantities, perhaps protected in deep subsurface reservoirs or under thick ice sheets at the poles, far, far longer than the original models predicted. And that dramatically changes the window in which life could potentially have existed on Mars.
The narrative of ancient Mars has just completely shifted from a dry, dead desert to a dynamic world of roaring rivers and massive lakes. We know the environment was capable of supporting these 16 megasystems that move 28,000 cubic kilometers of sediment.
It's a different planet.
It's a completely different planet.
Yeah.
So given this immense proof, the question remains the ultimate planetary murder mystery. Why did the water all go away? And why so completely?
It's not one single event. It was almost certainly a cascade of failures. There are likely 3 interacting mechanisms that led to the collapse of the Martian hydrosphere. And we really need to examine each leading scientific hypothesis, recognizing that they probably reinforced each other.
Okay, let's start with the big one. The one that dictates the fate of the entire planet. Hypothesis 1, the loss of the magnetic field and atmospheric stripping.
This is the fundamental difference between Mars and Earth. For a planet to retain a thick atmosphere and liquid water, it has to protect itself from the solar wind.
It needs a shield.
It needs a shield. Earth does this with its global magnetic field, its magnetosphere, which is generated by our churning molten core, our planetary dynamo.
And Mars had this protection early in its life, correct?
It did. But Mars is a much smaller planet, and because of its size, its molten core cooled far sooner and much more rapidly than Earth's did. As that core solidified, the planetary dynamo shut down, and that led to the slow dissipation of the protective magnetic field, probably starting around 4 billion years ago.
So what happens when that planetary shield is removed? When you turn off the umbrella?
The planet's upper atmosphere becomes exposed to the relentless bombardment of intense solar and cosmic radiation, primarily the solar wind.
Which is?
It's a constant stream of charged particles flowing from the sun, and it acts like a sandblaster on a molecular level. It physically strips away atmospheric gases, carbon dioxide, nitrogen, and critically water molecules, blasting them off into space over millions of years.
And we can see this happening even today.
We can. Current Mars orbiters, like NASA's MAVEN mission, are designed specifically to study this. They still detect this stripping process happening today, confirming that a huge amount of Mars's early water simply escaped to the cosmos, molecule by molecule.
So we confirmed that a significant amount of water was lost to space, which thinned the atmosphere dramatically. And that leads directly to the next consequence. Hypothesis 2, climate collapse.
The thinning atmosphere acted as a trigger for a catastrophic climate shift. Early Mars relied on gases, likely carbon dioxide and maybe some methane, to create a greenhouse effect that kept the surface warm enough for liquid water.
The insulation blanket.
That's it exactly. As the magnetic field loss accelerated the stripping of that atmospheric blanket, the pressure dropped and the greenhouse effect failed.
So the planet just got colder and colder.
It led to a runaway cooling effect. The atmospheric pressure dropped below what's called the triple point of water. That's the specific temperature and pressure where liquid water can remain stable. Any liquid water that remained on the surface would have either frozen solid or it would have quickly sublimated.
Meaning it went straight from a solid or liquid into a gas.
Straight to gas, unable to pool or flow. The atmosphere thinned and the planet was locked into a permanent deep freeze, making it physically impossible for those 16 megasystems to flow or persist.
Okay, so these two hypotheses account for the loss of surface water. But the sources also leave room for a huge portion of that water to still be around, just hidden away. Let's discuss hypothesis 3, geological burial, or the Great Hiding Place.
This is the optimistic counterbalance, and it's a critical consideration for future exploration. Scientists hypothesize that while a portion of water was stripped away to space and a portion was frozen on the surface, a significant reserve, potentially billions of cubic kilometers, migrated underground, and it remains there today.
So the water didn't disappear entirely, it just changed its state and location. It moved from the riverbeds down into the bedrock.
Yes. Modeling suggests that as the surface cooled and the atmosphere thinned, vast volumes of surface water sank into the subsurface, becoming groundwater. And because the Martian surface is now permanently frozen, there's a massive permafrost layer that extends far underground. This ancient groundwater became trapped and preserved as subsurface ice. It's protected from the solar stripping that's happening above.
And this is more than just a theory. It's a critical target for finding resources. Where are scientists looking for these buried reservoirs?
The evidence points primarily to two areas. Firstly, the planet's poles hold massive ice caps, and we know from radar measurements that there are huge layers of subsurface ice extending out from those caps.
Yeah, and the secondary.
Secondly, significant water ice is thought to be locked into subsurface sheets across the mid-latitudes, often just a few meters below the surface dust. And this provides a direct, tangible link to potential future resource exploration.
It's the whole field of in situ resource utilization.
Exactly. If we ever want to establish a permanent human presence on Mars, we need water. For life support, for growing food, for producing rocket fuel. And these buried reservoirs, which were originally fed by those 16 megasystems, they're our best hope for finding those resources. The rivers vanished, but the water they carried might just be waiting for us right below the surface.
It's incredible to think that the same water that curved those canyons billions of years ago might be the water we use to sustain human life there in the future.
That is the beautiful continuity of planetary geology. The history of the planet becomes the key to its future. The distribution of that ancient water, now stored underground, directly dictates where we might land and operate future human missions.
This has been a truly monumental deep dive into ancient Martian history. We have moved so far past the abstract question of whether water existed to systematically mapping the organization and the colossal power of its hydrological past.
It's a huge step.
To recap the incredible scale of the new findings, Mars had organized systematic river systems. We've mapped 16 major systems that produced an estimated 28,000 cubic kilometers of sediment.
And that volume, that single volume, accounts for a staggering 42% of the total fluvial work done on the entire planet. The value of this work is just immense. And this new methodology, the successful combination of legacy topographical data like MOLA and contemporary high-resolution imagery like CTX using these integrated GIS systems, it's a crucial new tool in the toolbox for planetary science.
It not only forces us to reconstruct Mars's past as a radically wetter, more dynamic world, but it also develops new, universally applicable methods for mapping ancient river basins on other potentially habitable worlds.
I mean, you could apply this to icy moons in our solar system or even to distant exoplanets one day.
It truly is a powerful picture of a completely different planet, a world of geological giants.
But as always in science, especially planetary science, every answer only opens up more questions.
Okay, so think back to the sheer efficiency we discussed. The researchers successfully mapped 16 drainage systems that account for 42% of the global flowing sediment volume.
So here's the provocative thought for you to carry forward from this. What stands out to you about the remaining 58%?
That's right. Over half the work is still unaccounted for, in a way. that 58% of global fluvial work was done by systems that were either too small, below that 105 square kilometer baseline, which would mean they were vastly more numerous but less dominant, or, and this is the really fascinating part, that 58% represents systems that are currently buried, completely invisible to our current orbiters, perhaps waiting under centuries of dust or kilometers of volcanic rock.
This research doesn't close the book on Mars's wet history at all. It confirms that we have mapped the main highways, but a much larger, as yet unmapped hydrological history still exists, potentially including even more ancient or protected futures.
That missing 58%, that's the true frontier of Martian discovery.
An organized planetary-scale system that produced nearly half the erosion, and a vast unknown majority that still waits to be mapped. The deep dive continues.